Hello everyone, I'm Ravi from Apple. I'm very excited to present our work on learning to rank intents in voice assistants. Before I start, I want to acknowledge the contributions of my co-authors, Vasu and William. The agenda for today's talk is I'll go through the research questions we try to answer in this work and describe some of the components of a voice assistant. I'll describe energy-based models and our energy rank algorithm. Later I'll present the metrics and the datasets we use in our experiments and go through the results. And finally, we'll conclude with the summary. Now let's go through the research questions we try to answer. How can we handle some of the ambiguous user requests by leveraging information state in addition to language understanding that naturally occur in human interactions with a digital assistant? Since the pipeline architecture is prevalent in building large-scale virtual assistants, we try to answer the question if we could efficiently encode features from disparate models performing different tasks. And finally, we wanted to analyze the impact of applying energy-based models to learning to rank applications. Next, let's look at the pipeline structure that is commonly used with large-scale voice assistants. A voice assistant is formed of a number of components, one that transcribes the user's speech, also known as automated speech recognition, one that understands the transcribed utterances, also known as natural language understanding, one that makes decisions, also known as DM in short. But this subsystem, in addition to using language understanding features, also relies on information state to make better decisions. And one that produces the output speech, also known as text-to-speech or response generation module, followed by some downstream application that is specific to a task. Now let's go through the task description and examples of various ambiguities that may occur in user requests. The final goal of a voice assistant is to understand the user intent. Oftentimes, the exact meaning of the words is not enough to choose the best intent. We classify the information state into three categories. The first one is personal information. Examples are user location, app subscriptions, browsing history, etc. The second one is user state. For example, if the user is driving at the time of user request, etc. Third one is context. For example, dialogue context. The user said in previous queries in the same conversation or task, like song requests. Semantically similar requests can have different intents too. Consider the two cases. For the example on the left, user meant to play some song from a specific artist. However, for the example on the right, although playing some song from the requested artist is also reasonable, knowing that there is a song named One from the artist leads to better intent selection. Ambiguity can still remain even if a subsystem correctly decodes the user input. For the example shown, it is not possible to predict the user intended transcription unless we know there is a contact with that name, and this ambiguity occurs due to the homophone. Choosing the wrong transcription leads to the execution of a suboptimal intent even if there was a better intent. We term this scenario as an undesired dead end. However, if we can infer using the information state the correct transcription, then we can improve the intent accuracy. Now let's talk about energy-based models. We posed a problem of finding the correct user intent from a list of NLU decoded intents as a ranking problem. Traditional ranking solutions employ discriminative methods. As we have shown earlier with examples how information state complements natural language understanding, our solution is to learn an affinity metric that captures correlation between the relevance and executability aspects of an intent. We do so by associating a scalar energy measure to each configuration of the variables. This learning framework is known as energy-based learning. This framework is successfully applied in major financial and consumer-based applications like signature verification, Face ID, etc., and we adapt energy-based learning in ranking algorithms for the first time. Energy-based models, in short EBMs, assign unnormalized energies to all possible configurations of the variables. And this is an advantage over traditional probabilistic models since there is no need for estimating normalized probability distribution over the input space. Since there is no need of normalization, this saves us from computing partition functions which are expensive to compute. And also, EBMs are good at capturing correlations. Our ranking algorithm, Energy Rank, which is based on EBMs, consists of two phases. Phase 1, Pretraining, and Phase 2, Learning the ranking function. Since models in decision-making subsystem consumes input from multiple subsystems, two aspects are important: robustness of the features and efficient handling of multi-source inputs. Denoising autoencoders, in short DAE, is shown to be robust to variations of the input. In our case, we have three data types in the input: model scores that are produced by other subsystems, text generated by ASR and language models, and categorical features generated by natural language understanding models, such as sequence labels, verbs, etc. We start by modeling each data type, shown in light green layer, by adding affine distortions, shown in light magenta, followed by a separate two-layer projection, shown in dark magenta, of the encoder. This gives separate encodings for each data type. These latent representations are then fused to obtain the final representation, shown in light yellow. This final fused representation is used to reconstruct the denoised original inputs. We learn the parameters of the multi-source denoising autoencoder by minimizing the average reconstruction error captured by categorical cross entropy. The ranking function is learned by finding the parameters W that optimize the suitably designed ranking loss function evaluated over a validation set. Directly optimizing the loss averaged over an epoch generally leads to unstable EBM training and would be unlikely to converge. The ranker consists of two identical bidirectional GRU networks, where one network accepts the fused representation from multi-source denoising autoencoder and the other accepts the information state. Learning the affinity metric is realized by training these twin networks with shared weights. This type of architecture is called a Siamese network. We train using both pairwise and listwise ranking loss functions and report the results. Let's take a look at the metrics and datasets we use for our experiments. We evaluated energy rank using two metrics, error rate and relative entropy. We employed relative entropy, given by the equation shown, to quantify the distance between input score distributions P and Q. Relative entropy serves as a measure for the robustness of the model to upstream subsystem changes. A value of 0 indicates identical distributions, while 1 are maximally dissimilar. We use two datasets, a labeled and an unlabeled dataset. The labeled dataset contains 24,000 requests and is comprised of 7 domains. We use this dataset to measure intent error rate for the models. The unlabeled dataset is comprised of two sub-datasets sampled from two different input distributions. Each sub-dataset consists of 80,000 requests. We use this dataset to compute relative entropy metric for the models. Now let's look at the experiments and analyze the results. We trained three baseline models: logistic regression, lambda rank, and hypothesis rank, which we refer to as hype rank. The table here shows the results on the labeled dataset with 95% confidence intervals. We use a two-sided t-test to compute the p-value to establish statistical significance. We can note that use of information state improves the error rate. The superscript of lambda-mart denotes the encoding scheme used: OH for one-hot, FH for feature hashing, AD for eigendecomposition. Energy rank superscript denotes the pairwise function: EF for exponential function, HF for hinge function, LF for logistic function. And the subscripts denote pairwise or listwise loss paradigms. Energy rank, using information state, while employing logistic function and pairwise loss paradigm, performs the best. We then run the best performing methods on the two unlabeled datasets, each of size 80,000 samples from different feature distributions. Hype rank is fairly affected by changes in input distribution, while lambda-mart is less affected with 0.168 relative entropy. And energy rank, in addition to outperforming other methods in error rate, is more robust to input distribution changes with relative entropy at 0.112. In summary, we presented a novel ranking algorithm that is based on energy-based modeling framework. We described a pre-training approach that employs denoising autoencoder, which is effective in learning robust fused representations for multi-source input. And finally, we evaluated our model against other alternative methods and established our approach is more robust as measured by relative entropy. Please check out our paper, and we would like to thank our colleagues for their support, guidance, and advice.